While siRNA shows a lot of promise and has a wide variety of potential uses, it also has numerous limitations that hinder it. siRNA made naturally by our cells is usually quite effective and doesn't suffer from any of the delivering or targeting issues as it's made in the cells that it's required in. This is not the case when we try to artificially use its power. In the figure below, you'll see a list of some of the common issues we encounter when trying to use siRNA for our own purposes. This list can be extended to siRNA is naturally degraded by endo and exonucleases in the cell, and this is true for all RNA. It doesn't remain long in the cytoplasm. siRNA in blood only lasts 6 minutes without modification, and in most cases that's just not long enough to get to the target tissue in the one that we desire it to be in. In the case of miRNA, they share a partial homology with the 3' untranslated region of most target mRNAs, and this can sometimes lead to off-target effects and unintended suppression, which is really not good. siRNA itself has no inherent tissue-specific targeting abilities when within the blood or when in other tissues, and so it can take unwanted effect in places where it should not be. Genuinely, molecules existing in the blood less than 50 kilodaltons are subject to renal clearance and filtered out of the kidney, and blood actively removes any naked nucleic acids such as RNA or free DNA. Importantly, if siRNA is made longer than 30 nucleotides, it will lead to the production of interferon via a toll-like receptor, and this will suppress all genes within the cell, leading to total cell death, which is why we always make our siRNA 20 to 29 nucleotides long. So in order for siRNA to become a therapeutic tool, we must overcome these issues. siRNA cannot be delivered orally, and if it's injected straight into the desired tissue, their research has found that there are often unintended side effects and off-target effects. So it must be introduced in the blood. This is an issue because, as we already previously stated, it only lasts 6 minutes in the blood when unmodified before enzymes degrade it, and it has no way of targeting tissues or organs. Therefore, it must be contained within something and or be modified to be able to find its way to the desired tissues. To do this, we've devised various methods that all impact the properties of siRNA in different ways, and these are but are not limited to cholesterol conjugated siRNA, which is where it is joined to a fat molecule essentially, aptamer, which are single stranded nucleic acids, siRNA chimeras, where they are joined together, and this improves targeting. These can be ribose sugar alterations, where we add different molecules to the two carbon sugar on ribose, as it was found that the 2-carbon sugar can be altered without having any effect on the siRNA. And hairpin and dumbbell siRNA are molecules made where the overhang is increased on one side and then it comes around to join to the other side. And these all impact and improve the targeting or longevity properties of siRNA.